So chapter 9, problem 61. So with this problem, let's just read it real quick. A 50-story building is being planned. It is to be 180 meters high with a base 46 meters by 76 meters. Its total mass will be about 1.8 times 10 to the 7th kilograms, and its weight, therefore, about 100 times more, which is 1.8 times 10 to the 8th newtons. Suppose a 200 kilometer per hour wind exerts a force of 950 newtons per meter squared over the 76 meter wide face. And what we want to do is calculate the torque about the potential pivot point, the rear edge of the building, the bottom left, where the force from the earth acts, and determine whether the building will topple or not. And we can assume the total force of the wind acts as the midpoint of the building's face and that the building is not anchored in bedrock. We're also given a hint in the problem, but I'm not going to read that. So let's just get right into it. If we assume that the building has just begun to tip so that it is essentially vertical, but that all of the force on the building due to contact with the earth is at the lower left-hand corner, then we can draw a figure like this. Our building right here on this corner, so we can imagine here, and I'm just going to blow this up a little bit. It's going to look like this. From the right on the corner, we're going to have a force going up and to the right to match our earth force that was diagonal originally. So this is going to be Fex, and this is Fey. And this is Fe. The diagonal is Fe. So if we take torques about that corner with counterclockwise torques as positive, so it's going to be counterclockwise is going to be positive, clockwise will be negative. Then what we can do is the Newton's second law, but in rotational form. So sum of the torques is equal to I alpha, but we can't say whether this is zero or not because we don't know if it's definitely non-zero actually, because we know that the building is starting to tip over this way, right? The air is pushing it here. So knowing that it's non-zero, we don't really need to know what this is as long as we know what the sum of these torques. All we really want to know is the sum of the torque. We don't really want to know the specific moment of inertia or angular acceleration. So let's just do that. So sum of the torques, we have a torque produced from the force of the air pushing leftwards. And so since we have counterclockwise as positive, anything going in that direction, like the left direction, is going to be positive. So a torque is determined by, well, let's just write a general formula for torque first, real quick. Okay, so torque is normally defined, the vector torque is defined by position crossed with force. But if we're just talking magnitudes, then this is the magnitude of the position times the magnitude of the force times the sine of the angle between them. And so this is what we're going to be using, but in this problem, every angle between the force and the distances are 90 degrees. So sine of 90 is just 1, and we won't be dealing with sine. We're just going to have distances and forces. So just drawing that again, sum of the torques is going to be equal to the force of the air pushing left, and the distance associated with that is going to be halfway up the building, right? So if we go back here, if we go to the center of the building, we said it was 180 miles tall, so if we just half that, we get our 90. So it's going to be that force times the distance it acts at minus the gravitational force multiplied by its distance. So that was 46, if I'm not mistaken. So half of that is 23. And with this, we have our torque. So now we just need to plug in the numbers and calculate. So this is, we know this force earlier, 950 newtons per meter squared times 180 meters times 76 meters. Because we're dealing with an area here, so this squared is important that this squared has to cancel out with this, with these meters. So specifically, let's see what we meant by this. Right. So there's a 200 kilometer per hour wind that exerts a force of 950 newtons per meter squared. So this is actually a good word to call this is like force flux. It's like force happening through an area. So we want to get rid of this area by multiplying by an area, which would be a length times a width, right? Which is what we do here. So now that we've done that, we get our newtons out only. And then what do we want to do next? We have one more torque. The other torque being 23 times mg. So that's basically just 23 multiplied by, so we're subtracting 23 multiplied by 9.8 meters per second squared times the mass of the building, 1.8 times 10 to the 7 kilograms. So this is our mass, and then this would be our weight, right? Then equals to minus 0.29 times 10 to the 9th Newton meters, which is a torque. Since this is a negative torque, the building will tend to rotate clockwise, which means it will rotate back down to the ground. So we're saying that if we started assuming that the building was going to fall to the left, we did our calculation that even with this wind, the building will tend to rotate clockwise because of the torque because of the force from the floor. There's a torque acting on the building that will keep it going to the right, and so the building will not topple.